Yes, can someone tell me what was our point of discussion in the previous class? Suhas, yeah, Suhas, can you answer that question? Kishan, Suhas, yes,
So,
yeah,
first class with modality with time and orbits
okay.
and orbit VTC.
Hmm.
That is I
Okay, so we had started off with the discussion of orbits, right? And
yes, sir.
we were also discussing the geostationary orbits. Yeah? Okay, so I will put up. Thank you, Kishan. I'll pull up the notes and we will start our presentation. So we have to start off with something called antenna look angles, right? Okay, and just for recalling few things, we had seen the geostationary orbit, right? And there are few conditions that needs to be maintained while having a geostationary orbit. So what are those three conditions? The satellite must travel eastward and should have the same rotational speed, and the orbit must be circular. It shouldn't be any other uh, way. Of course we know that it's not going to be a perfect circle, right? And the inclination, okay, the angle of inclination I should be 0. So these are some of the things. If in case there is an angle, then we call it as inclined orbits. Okay, we have seen that previously. Inclined orbits where there is an angle of inclination that has got created and that doesn't correspond to your geostationary, right? Okay, so today we will be actually looking into something called antenna look angles. Okay, so as I told you, um, in what angle the antenna should be placed and how these are to be maintained in order to have maximum reception of signals. Okay. So the look angles for ground station antenna are the azimuth angle and the elevation angle. Now these two terms will be extensively used throughout our course. Okay, azimuth and elevation angle. So we will see them in detail as to what they are, how and when these angles are created, and how do we actually extract data in calculating these angles. Okay, these angles are required so that it points directly at the satellite. I've given you the example of our you know dish, which is actually placed, okay, in such a way that the maximum reception of signals happens. So we should we should be placing this dish in such a way that there is less noise. That is why you get those meters attached, okay, before we get it installed. Okay, those meters are attached and it actually checks for the reception. If it's greater than 90%, then it's good, right? It's in the green zone, so it's greater than 90%, which means it's receiving maximum signal. Of course you cannot attain 100%. The reason is because of these atmospheric losses, the atmospheric pressures, and all the other things that comes into picture. But what I would like to say is without these or these signals, okay, cannot be attained the whole 100%, okay, all because of the losses that can happen. Now the look angles were determined in general case of an elliptical orbit, and uh, there the angles had to change in order to track the satellite with the geostationary orbit. The situation is much simple because the satellite is stationary with respect to Earth. So since that's the reason, we are actually placing it in geostationary orbit. That's why I was telling you it is regarded as a natural resource because every country wants to put in their satellite in that orbit, right? So there's only one orbit, and if all of them are racing for the same, then it actually becomes a resource. Next, the look angles are determined in the general case of an elliptical orbit, and there the angles had to change in order to track the satellite. Okay, so this was with regards to inclined orbits. So inclined orbits, the angles were not stationary, but instead it was having an angle of a slight angle wherein they were not able to actually position the satellite properly, and the antennas were not able to face the satellites in proper direction. Okay, there are some information or important notations, okay, that needs to be kept in mind. So just have a look at those. The Earth station latitude, which is denoted by lambda e. 5e is your Earth station longitude. Okay, this is nothing but your latitude and longitude are your imaginary lines that are drawn across the planet. Okay, so why is this done? So that you can actually get the exact coordinate. Now when you get into your Google Maps, you have something called plus. Okay, wherein you click on that plus symbol, the sign code, okay, plus. So that will actually copy the address, and every place will have its unique address, unique coordinates. Similarly, we will be using these latitudes and longitudes in order to uh, measure or find out where this antenna is positioned, and accordingly we can uh, place it in a proper way so that it starts maximum reception. Okay, the longitude of subsatellite point is denoted here by phi ss. Okay, this is referred to as the satellite longitude. Okay, so phi ss is your longitude of subsatellite point. Okay, so we will see as to what these are with the help of a diagram. Now, as I've always told you, the center of the Earth is a very important uh, point to be considered for our calculation of elevation angle and azimuth angle. Okay, so let's assume that this is a satellite. Okay, and from the center of the Earth, you draw one line. Okay, and you just take a line A. Okay, which is in the north and east region. So, okay, we will take it one by one. From the satellite, draw a straight line on the northeast plane. Okay, from the satellite, you should draw a straight line from the northeast plane. So you will get a point. So this point, you can connect it to your center of the Earth. You will get point A. So we need to note down the angle that point A makes with the north. The azimuth angle, okay, is the angle that gets created between this point A and the satellite. So we have a satellite here, we are putting a straight line, okay, and we are trying to connect it to the center of the Earth. The azimuth angle is the angle between the north towards the east where the satellite point falls on the plane. Okay, when the satellite point falls on the plane, so exactly in the northeastern plane, we should draw a line, okay, an imaginary line, and then connect it to the center of the Earth. So we'll have 2 points here, okay, point A and the center. Next, the uh, Yeah, this is the angle of elevation. Azimuth angle is to the northern plane. Okay, the angle that gets created with the northern plane. See, you have north and east plane. Okay, fine. Elevation angle is vertical. It is from center of the earth, the angle between the satellite and point A. So as I was mentioning, you have a satellite, you have dropped a point A and then to the center of the earth. Okay, so the angle that gets created between the satellite and point A is the angle of elevation. So the higher the satellite goes, the higher is your angle of elevation. And the other angle that gets created is the azimuth angle, which is with respect to the northern plane. That is also with reference to your center of the earth and the northeastern plane. So these two, okay, the azimuth and elevation angles provide instantaneous position of a satellite. Okay, so using this azimuth and elevation angle, we can exactly know how high the satellite is and at which point it is, and how much angle that it's creating with respect to north and eastern plane. Okay, so these are now some of the important parameters that you have to consider. The earth station latitude, which is denoted by lambda e. Okay, and the earth station longitude, which is denoted by phi e. Okay, similarly we have the sub satellite point phi ss. Radius of the earth, which is constant, is denoted by r. Okay, and you will have the distance from the center of the earth called d. Okay, from the center of the earth called d. Of course, I'll be showing that in the other diagram. And then you'll be having the radius of the orbit, okay, which is AGSO. Okay, geostationary orbit, and the radius a. Okay, so all these are the important parameters for your look angles. Okay, so these are actually needed for calculating our look angles. Okay. Now, why is it so necessary? So that we can actually position them in such a way that we get to know what is the angle that gets created with the center of the earth, and we can also find out exactly how much angle it's creating between north and eastern plane. Okay, fine. So we will be using all of these extensively. Okay, lambda e, phi ss, r, and d, and agso, all this. Okay, so lambda e is nothing but the latitude, earth station latitude. Phi is your longitude of earth station. So earth station e, it is represented with the subscript e. Okay, lambda is nothing but your earth station, and phi is nothing but your uh, longitude. Okay, so you can keep that in mind. Next, if I use something called ss, okay, so that becomes your sub satellite point. Okay, and r, there's no confusion, radius of the earth, and d is the distance, and a is for geostationary orbits, radius. Okay, fine. Now all those points which I told, okay, are actually summed up in this diagram. Okay, so CE is nothing but your center of the earth. From the center, if I draw a line, okay, so that becomes to the circumference. Okay, to the circumference, and that is nothing but your radius, right? And then um, you have your sub satellite point. Okay, so you the satellite, from the satellite to the center of the earth. Okay, the center of the earth, that is nothing but called as d. Okay, then r is the radius. Fine. Okay, and this is your subsatellite point. Okay, so as I mentioned to you, CE is nothing but the center of the earth. Okay, ES is the earth station. Okay, so somewhere we have our earth station located here. Okay, of course we all are not here, we are on the outside, on the circumference, right? We all are on the circumference. So the earth station is located, let's say it's located somewhere here, and S is the satellite in space. Okay, this is some satellite which is in space, and draw a line from the center of the earth to the satellite. The place where it intersects the earth is a special point, and that is called your uh, sub satellite point. So from the center of the earth, if you take from the center of the earth to the satellite, okay, that becomes your sub satellite point, and that is in fact denoted by another letter called d, distance from center of the earth to the satellite. Now we are not taking from the uh, from d is actually not from the uh, from the circumference. Okay, it's actually from the center of the earth. Sub satellite point is actually from your circumference. Okay, so now yes, there's a explanation here that you can make note of. Sub satellite point, uh, that's a special point. Okay, and if we are standing over sub satellite point, the satellite is directly over our head, so which means we are exactly drawing a line, and it should not make any angle. Okay, there should not be any deviation when the satellite, we should think that the satellite is exactly on top of our head without making any angle. So that point, so which means I'm just drawing a straight line from the satellite. So once I get this point, this is called a sub-satellite point. If I extend that to the center of the earth, that becomes d. Okay, okay, sub-satellite point, which is actually straight. Now r is a constant, which is nothing but the radius of the earth, which is 6378. Sometimes we'll have to remember this value, and if in case the value is mentioned in the question paper, then fine. If not, most of the times these values will be uh, kept as standard values, and you will be asked to assume. Okay, so 6378, you have to remember that. Okay, so next we will look into something called longitudes and latitudes. Okay, so if in case a question is asked, uh, what is a longitude, what are latitudes, this of course we do know that it's a imaginary line drawn across our planet. Okay, so longitudes are having 0 degree at Greenwich meridian. Okay, and it is having greater than 0 degree when it's moving towards the east of Greenwich meridian. So this is kept as a reference. Okay, the Greenwich meridian is kept as a reference, and it has less, or it goes beyond, or it goes in negative degrees. Okay, when it moves in the opposite direction. Okay, so when moving towards the east, it creates a positive degree, and when from that point if it's moving towards the left, okay, then there is a negative degree that gets created. Okay, so exactly at Greenwich meridian point it is 0 degree. Fine. Longitude 0 degree is at Greenwich, England. If we have positive values, we are moving towards the east. This is very important. Okay, so if I say positive longitude, so immediately you should imagine that from your Greenwich meridian point, you are actually moving towards your east side. Okay, and it is true for the opposite, negative values. which means I'm moving towards the west from that point. So this is with regards to longitudes. Now let us see exactly with regards to latitude. So this is with reference to the equator. Okay, 0 degree at the equator. So now we have seen east and west. Okay, so we have to see now north and south. So it goes greater than 0 when it is in the northern hemisphere. So from the equator, if you are actually going up, okay, towards the north, then it creates a positive angle. Okay, so that means it is going beyond 0 degree, greater than 0 degree. When you're going to the southern hemisphere, okay, so when you come exactly at the equator, okay, that will give you 0 degree, and if you're coming down to the south, okay, then it gives you a negative value. Okay, so ultimately you should be able to understand as to based on the values, okay, if it's positive or negative, and if it's longitude or latitude. Based on this exactly you can coordinate things. Okay, so that's what I have re-emphasized here. I have put latitude 0 degree, equator greater than 0, which means northern hemisphere. Okay, latitudes will be taken as positive angles. Okay, this is important, positive angles. Then 0 degrees, less than 0 degree, it's going southern, and those are negative angles. Okay, so this is important. Fine. Now you can have questions like this. Okay, calculate. You will have to calculate the angular, the antenna look angles. So example, they will give you 40 degrees south. Okay, so if I give you like this, then you should actually take it as minus 40 degrees. I hope you all are understanding, right? So whenever there is a south here and whenever there is a west, I will be taking minus. Okay, so that's the concept of your longitude and latitude. So longitude refers to east and west, and your latitude refers to north and south. And if I give you a longitude of 35 degrees west, so which means I have to take it as minus 35 degrees. So I hope this concept is clear, students. Any doubts, please feel free to ask me. Any doubts, students? You all able to follow? You can even use the chat box if you have not understood the concept. Is the concept clear as to how we are using positive and negative angles here? I need a confirmation.
Yes, I can understand.
Okay, fine. Thank you. So now that we know how to represent positive angles and negative angles, and is it towards the east or west or north or south? Okay, so we will go ahead and we will see few more information. Okay, so your angle of elevation. Okay, so EL in short can be represented as cos inverse EGSO. Now what is EGSO? Is the radius of your geostationary orbit divided by d. D is nothing but here the distance from the center of the earth to the satellite, okay, into sine b. Okay, where d is equal to, now specifically for the center of the earth, from the center of the earth to the satellite, we have another formula, r square plus r is your radius of the earth. Okay, then AGSO square minus 2 times r AGSO into cos b. Okay, so you should actually remember all of these terms which we talked about. Okay, lambda e, phi e, phi ss, r, d, AGSO. So these are important parameters to find out the look angles. Okay, so let phi s and phi ss be the latitude and longitude of the sub-satellite path. Okay, so as we saw previously, 5s and 5ss. Let lambda e and 5e be the latitude and longitude for the es, which is nothing but your Earth station. B, okay, B, the capital B, remember it's not small b, capital B is equal to 5e minus 5ss. Okay, 5e is nothing but your longitude for your Earth station, and 5ss is your latitude for your sub-satellite point. 5ss is the longitude of your uh, yeah, sub-satellite point. Then we have A. These are all standard formulas. You will have to remember this formulas: angle of elevation B, okay, and A is equal to sine inverse. Once we find out these values, okay, this value of B should be actually substituted here. Okay, so then we have small b, right? Small b is nothing but here cos b, okay, into cos lambda e. Okay, cos b here is your big capital B. Okay, or we can also use r cos b cos lambda e. So this also can be used. So these are some of the important formulas to be actually kept in mind before we proceed into some problems. Okay, so here you can actually understand, just like how I had represented my handwritten diagram, I thought I will show you here also. Okay, where you will have a sub-satellite point. Okay, the azimuth angle towards the north, earth station. Okay, so these are different v's. Okay, your sub-satellite point in the northeastern plane, the northeastern plane of earth station. Now keep that in mind. You cannot just take northeast of anything. It is northeast of your earth station or your base station, wherever your base station is located, because you are calculating with reference to your base station. Okay, then your sub-satellite point is northwest of, which means I am just rotating it the other way. Okay, this comes the other way. So this becomes your northwest of Earth station, because Earth station was here and now I shifted here. So the diagram wholly changes. And similarly towards the ES, okay, southeast of ES and southwest, how it changes. Okay, just a few diagrams so that it's easy for you to understand. So there are some standard values, okay, to be actually kept in mind. Remember, I told you the value of A, B, C, D. Now, whenever your lambda E is less than 0 and when B is less than 0, okay, your azimuth angle, okay, the azimuth angle, it is represented as AZ, is A. Suppose in the next case, okay, it's less than 0 here and greater than 0 with case B. Okay, what is this B? See, B is this formula. Okay, and what is A? Okay, what is lambda E? Lambda E is nothing but for your earth station. Okay, fine. So here in this case we'll have to minus 360 degree from the azimuth angle. So these are some of the changes that we have to do while calculating the problems. Lambda E is the latitude of earth station, okay, and B is the difference between the longitudes of earth station and SSP, which is sub-satellite point, as I showed you here, right? 5ss minus 5e earth station and your sub-satellite point. So these are some of the things that you will have to remember. Okay, so you can have a problem like this, okay, where yeah, of course we will be looking into this problem in detail in the next class. I will just give you a glimpse of what we are going to solve in the upcoming class. Okay, so we have a geostationary satellite which is about 90 degrees west. Keep in mind, when it is west you'll have to put a minus, when it is south you have to put a minus. find A and azimuth angle. All these are asked. So how will I go about? I will take the formulas. I will first extract data, okay, using my values, okay, cos values. I will find out, and then once I get those, I'll be putting them into standard formulas. I check for this combination. Remember I told you a tabular column here, right? So we will be using the tabular column here, and then accordingly I will be calculating the azimuth angle. So we will solve this in detail. Okay, so as of now you remember how to calculate azimuth angle. uh, how are these angles seen with the different planes, north, south, east and western plane, okay, uh, and these formulas. So I think we will stop our class here and we'll continue in the next class. Any doubts so far, students? Is it all fine? I'll be sharing in the link in some time in your classroom, and you all can give in your attendance.